I want to review with you square roots, which is an algebra lesson that you should have some familiarity with, but maybe you haven't seen it presented this way before. And so this is a skill that we're going to need to use in geometry, so it's a valuable one for us to take a pause and review right now. So this particular video, I'm just going to go ahead and take some notes. You're going to copy those notes down, kind of keep your learning going. If you need extra time to write something down, just pause the video, write it down, and then you can continue. So name and period number upper right, and then here's your title, Working with Square Roots. So I want to kind of just start to break this whole thing down. So let's begin with just the basics of squaring a number. Squaring a number. All right. So when we talk about squaring a number, that might look something like this, where we take this number and then we write this little smaller number to the upper right. Of course, this number is called the exponent. This number is called the base. And the idea behind this is that the exponent tells us how many times to multiply the base by itself. So the base is 3, the exponent is 2. That means 3 times itself, 2 times. So this 3 squared breaks down to the math problem, 3 times 3, which is 9. That's all pretty basic. Most of you should be pretty familiar with that. Let me give you the geometrical idea, because, we talk about this idea of squaring a number. It's got a very geometrical sounding idea to it. And it is, in fact, let's do this. Take up 3 lines of your paper and just kind of draw a line down like this. We're just sketching now. You can use a ruler if you want, but this is just a quick sketch. So we're going to draw a square here like this. And we'll cut across our lines like that, and then we're going to cut down here, and we're going to cut down here. So you can see that I've created this square, and this square is 1, 2, 3 units tall, and it is 1, 2, 3 units long. And of course, if we wanted to figure out the area, which is how many 1 by 1 squares fit inside this shape right here, then we would be talking about 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 units. All right, now we need to make this connection. To find area, right, we multiply base times height. So that's the 3 times 3. We come up with 9. There's 9 little squares in this shape here. And so really what we're finding when we square a number is we're finding the area of a square. All right, now that's where this whole idea comes from. When we square a number, we're actually finding the area of a square with a side length of the base. So let's write that down, because that's an important understanding of what this actually means. So I'm going to go ahead and put a little asterisk here, and we're going to jot this down. So when we, and we'll put this in quotes, square a number, what we're really doing is we are finding the area of an actual square. So like the shape, a square, we're finding the area of an actual square. Let's kind of underline that right there. Where the number, this is the one that we're squaring, right? Where the number we're using is the side length of the square. So when we square a number, we are finding the area, right? The area, this number in here, we're finding the area of an actual square where the number that we're squaring, that would be the 3 in this case, is a side length of the actual square. So you can see that this 3 is a side length. So when we're doing 3 times 3 and we get 9, that 9 is actually the area of a square with a side length of 3. Real important that you understand that concept. Visually, if you get that idea, then more of this is going to make sense as we move through, okay? So let's talk now about square rooting a number, all right? So we're going to come down here for the next section, and we're going to talk about square rooting a number. And what we want to say about square rooting a number is that it is the opposite of squaring a number. So just like subtraction is the opposite of addition and division is the opposite of multiplication, square rooting is the opposite of squaring. All right, so these are opposite operations. Okay, then that gives us something to work with. All right, let's kind of put this in terms of our little diagram that we had up there. So if square rooting is the opposite of squaring, really what we're doing is we're starting with the area of a square, and we're being asked to find the side length. Being asked to find the side length of the square. Right? If you think about that, it makes sense, right? So when we squared the number, we started with the side lengths and we had to go in and try to figure out the area. So when we're square rooting, if we're doing the opposite, then we're going to start with the area of the shape and we're trying to go back and figure out what is this value out here, the side length that produced that particular area. All right, so let me show you the symbol. You should be familiar with this. You've seen it before. Whoops, that's not what I want to do. Let's get that put away. Put by. All right, so let me show you the symbol. It looks like a division sign with a little hook on the front like that. And this symbol right here that I'm highlighting for you, that symbol right there is called a radical symbol, and it asks a specific question. So let's jot that down. We're going to put this up here. Again, just kind of getting this idea that when we have the radical symbol and we have some value inside that radical symbol, that is asking us a math question. What it's asking, this asks, what is the side length of a square with an area of, I don't know. That's the idea. So when we have this symbol and some number inside, the symbol is asking us what is the side length of a square with an area of whatever number is inside here. So this particular question that we're working out right here, then the square root of 16 is really asking us to do this. Let's draw a picture of it. So we'll go 1, 2, 3, 4 lines down and then come across about the same amount, come down like this. And let's make square, cut it in half again, like that, right? So this particular shape has an area of 16, right? We can see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, but it's a square, right? And as we're learning about in our parallelograms, that means opposite sides are congruent, right? So that means that it's got to be a 4 by 4 square. So then we would say the square root of 16, what is the side length of a square with an area of 16? Well, the answer to that is 4. Okay, that is our side length. Let's make a note of that again just one more time. I want to really stress this idea of working with this geometrically. Okay, so this idea of squaring a number is when we take a side length and multiply it by another side length to figure out the area, that's squaring. And when we do the square rooting process, we're starting with the area and working our way back to figure out what is one of the side lengths. Okay, so the whole idea is that when we take a square root of 16, yeah, it came from 4 times 4, but the answer to this problem is 4 because we just want a singular side length. Okay, all right, so that's the connection between squaring and square rooting. Okay, back your paper or next page. So let's talk about something that we can call an imperfect square. You've heard of perfect squares before. Perfect squares are numbers like 9, 16, 25, 36. These are easy numbers to find, 2 numbers that multiply to give me that, right? The square root of 81 is 9, right? Because 9 times 9 is 81. But what about if we have a problem like this? What if I gave you the square root of 12? Well, that's a little bit harder to figure out, right? I mean, let's just kind of just scratch out a square over here. You know, we're not gonna break this one up into pieces. It'll be too hard to do. But let's just say that the area of this square is 12. Okay, well, we know that if this is a square root problem, right? I mean, this is still asking what is the side length of an area that of a square that has an area of 12. Okay, well, that means that it's some number and it's the same number here, right? We need to multiply those two numbers. Now we got to figure out what are those numbers. All right. Well, when we're dealing with something that doesn't have a nice, neat, perfect square like 36, like 49, like 100, those kinds of numbers, what we want to do is we want to use our prime factoring tool. All right, so I'm going to take you back a little bit to kind of grade school where we did our factor trees like this, and you can put any two numbers that multiply to give you 12 down here. But the goal is that when we get done doing as many trees as we need to do down our problem here, we want prime numbers, and prime numbers are numbers that are itself times 1. Those are the only possible numbers. Let me show you what I'm talking about. So like, for example, I'm going to use 4 and 3. All right. 3 is a prime number because the only thing that could go on a tree down below that would be 3 and 1. Those are the only two whole numbers. So instead of having to write that every time, I just circle it because I know it's a prime number, and then I can just leave that tree off. However, 4, on the other hand, is not a prime number. That's a composite number. And that means that I can come up with another math problem other than 4 times 1. And that's 2 times 2. So I want to keep going with these trees until I get all prime numbers at the end of the branches. When every branch ends in a prime number, then I'm done doing what we call prime factoring. All right, we're basically coming up with another way to say the number 12 in terms of a multiplication problem. Watch, I'll show you what I'm talking about. I'm going to rewrite this square root of 12 like this. It's going to be the square root of 2 times 2 times 3. All right, these are the prime factors for the number 12. Right, so I'm just basically taking this and I'm rewriting it as a multiplication problem. But here's where it comes in handy. All right, now because we know that squares have to have two of the same numbers, right? We can look for pairs of numbers in our prime factoring, and we can remove those from our square root question, from our area question like this. So kind of the little analogy I like to use is sort of like a jailbreak. This is the jail, all right? And these are the prisoners inside of the jail, all right? And we've got, you've got to have a partner to try to escape. So you can see here that the 2 has a partner. There's 2 of them there. The 3, however, does not have a partner. So the 2s are going to try to make a run for it. So I'm going to circle my pairs of numbers. Every time I have a pair of numbers, I'm going to circle them. And what I'm going to do is one of those is going to escape the jail. And unfortunately, bad news for the other guy, he's going to get taken out. All right. So the way it's just sort of a little analogy I like to use. So in this particular case, for every pair of numbers that I have, one of them is going to get removed from the jail, and then the other one is going to be eliminated. All right. So in this particular case, you can see that the 3 does not have a partner. 3 is not getting out of that jail because he does not have a partner. He's stuck in the big house. But these 2 right here, one of them is going to get out. So when it's all said and done, what we end up with is a 2 outside of the jail, and we still have the jail, and we have a 3 inside of the jail. And so another way that we can write the square root of 12 in its simplified form, that's what we would call this, is 2 times the square root of 3, or 2 root 3. All right, now, if we continue with our analogy, this is a side length of a square, right? So really what we're saying here then is this question mark and this question mark really are 2 square root 3 and 2 square root 3. Now, that gets a little funky and a little weird to do because if we had to try to multiply these up and we're using irrational numbers, because you plug this into your calculator, you're going to get like long decimal numbers. But could we do this multiplication problem and verify that 2 times the square root of 3, so this times this, is going to give us an area of 12. And this is a really important skill that not only going to use in the parallelograms lessons, but you're going to use throughout as you continue to move throughout math, and as we get into trigonometry, this will be some important things. So let's do that, okay? Let's check and see if we actually came up with the correct side length, all right? Let's check and see if we actually came up with the correct side length here. So here's how you would do this. We're going to take 2 square root of 3, and we're going to multiply it by 2 square root of 3, just like we would have done with any of the other problems we did. All right. Now, there's something that I want you to know. When we write 2 square root of 3 like that, it's sort of like writing 2x. It's a math problem. Like this means 2 times x. I mean, another way we could really write this, even though it's not the kind of accepted way of doing it, is 2 times x like that, right? So we can do the same thing here with these. This is really 2 times the square root of 3 and 2 times the square root of 3. You could actually kind of think of it like, you know, there's a multiplication dot in between there like that. So if we broke this problem down, we could rewrite it like this. 2 times the square root of 3 times 2 times the square root of 3, like that. Now, multiplication, of course, we can reorder numbers and put things together. You know, order doesn't matter when we're doing multiplication. That's your commutative property of multiplication. So we could reorder this and go 2 times the square root of 3 times the square root of 3, like that. Now, when we're multiplying and we're dealing with square roots, the numbers that are outside of the jail get multiplied together, and the numbers that are inside the jail get multiplied together. But nobody goes in jail and nobody comes out of jail in these types of situations, these problems. So we would multiply the two 2's together. That would give us 4. And then we would multiply the two 3's together, but they would have to stay in the jail. So that would be 4 times the square root of 9. But see, now we're onto something right here, because 9 is a perfect square, right? I mentioned some of those perfect square numbers earlier, right? So, I mean, if we think about it, right, and just kind of a real quick scratching out over here, boom, 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 like that, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So a square with an area of 9 is going to be a 3 by 3 square, right? That means one of the side lengths is 3. So we can actually solve this square root now. That's 3. So we can actually now rewrite this problem 4 times 3. And what's 4 times 3? 4 times 3 is 12. And oh, would you look at that? As we come back to this problem, now you can see that the square sides that we found here, oh, I'm losing my, hang on a second, I lost my technical functions. All right, here we go. So now you can see that the side length 2 root 3 and the side length 2 root 3, when we multiplied those two together, following this process right here, we came up with the area of 12, which is the area of that square, which is where we started this problem right here. So being able to multiply square roots is an important skill, but understanding that we're talking about side lengths of actual squares and how they produce the area. And so when we square a number, we're multiplying side lengths to get area, and when we square root a number, we're starting with area to work our way back and find a side length. Important understanding as we continue to move forward.